Ever grappled with the complexity of handling high-dimensional data in data science? It's a challenge, isn't it? Well, the good news is there's a technique that can help simplify this process. It's called Principal Component Analysis, or PCA. PCA is a statistical procedure that uses an orthogonal transformation to convert a set of observations of possibly correlated variables into a set of values of linearly uncorrelated variables called principal components. Sounds complicated? Don't worry, it's about to get a lot clearer. Imagine a swarm of bees buzzing around in three-dimensional space. Each bee represents a data point, and the three dimensions represent three variables. Now PCA identifies the most meaningful basis to reorient the data, seeking the best angle from which to view it. This angle is the principal component. Step 1 in PCA involves standardizing the data. Standardization is crucial because it brings all variables to the same level of magnitude, which means the PCA will not be biased towards high-magnitude variables. Step 2 involves constructing the covariance matrix. This matrix captures the way all the variables in the dataset change together, because the principal components we're after are directions in feature space along which the original data vary the most. The third step is to compute the eigenvalues and eigenvectors of the covariance matrix. The eigenvectors represent the directions or components for the reduced subspace of the data, while the eigenvalues represent the magnitudes for the directions. The fourth and final step involves ordering the eigenvalues and choosing the top ones that contribute the most to the data's variance. The eigenvectors with the highest eigenvalues carry the most information about the distribution of the data. These are the principal components. In summary, PCA is a powerful tool in the field of data science. It reduces the dimensionality of data, simplifying complex data sets while retaining their most important information. The process involves standardizing the data, constructing a covariance matrix, computing the eigenvalues and eigenvectors, and selecting the principal components based on the highest eigenvalues. This technique is widely used in data visualization, noise filtering, feature extraction and engineering, data compression, and much more. However, remember that PCA makes the data easier to explore and visualize, but it doesn't always make it easier to interpret. The original variables morph into principal components, which are combinations of the original variables, and this can make interpretation tricky. So the next time high-dimensional data has you scratching your head, remember principal component analysis. It's a nifty trick to have up your data science sleeve.